Bode plot already we have seen that magnitude in frequency logarithmic scale. Frequency also in logarithmic scale. So any multiplication will become summation in logarithmic scale. Any multiplication becomes summation in logarithmic scale. That's why in a transfer function, if you break them into many factors, in the denominator is factorized and we are taking 2-3 factors. For each factor I am drawing separate frequency response. Everything in logarithmic scale. So if I add all the plots together, I get the total response. Because everything is in logarithmic scale. Everything is in logarithmic scale. That is the advantage of Bode. So if I take only one factor, I can easily draw the magnitude plot and phase plot for that. For each factor, I can separately draw the magnitude plot and the phase plot. If I combine all the plots, graphically if I add all plots, then I will get the complete plot. That's why we have to see how we can break the transfer function in so many factors. So if we see that, if we take a transfer function k divided by some polynomial in S. Numerator also sometimes they have polynomial of S. If you factorize that, what are the factors you get? In the denominator you get first order factors. Tau S plus 1. If you factorize that, how you will get? R S plus P1 in whole zero form. S plus P1. In time constant form, tau 1 S plus 1. Time constant form. So any transfer functions can be break into many factors. For example, I am taking a third order system. A third order system may be represented by G of S equal to k divided by S plus tau 1 S plus 1, tau 2 S plus 1, tau 3 S plus 1. It is third order system. So the denominator is factorized. So if I know the Bode plot for this k separately, if I know the Bode plot for 1 by tau 1 S plus 1, similarly 1 by tau 2 S plus 1, and Bode plot for 1 by tau 3 S plus 1, if I know, graphically all can be added. Graphically all can be added because both magnitude and the x-axis are in logarithmic scale. It can be added. Multiplication can become addition. It can be added. That is the advantage of Bode plot. First we have to do for each factor what is the Bode plot we have to see. So what are the factors it may contain? The constant k may be there. The integral factor, the denominator polar to origin means it will be S factor in the denominator. So S that is called polar to origin or multiple polar to origin. Suppose in the denominator S square is there means 2 poles at origin. So for that what is the Bode plot? The derivative factor S in the numerator. For that what is the Bode plot? S square or S cube, S power n in the numerator. What is the Bode plot for that? First order factor in the denominator. Already I mentioned 1 by tau 1 S plus 1 or 1 by S plus P1 in whole zero form. For that what is the magnitude plot? Bode plot. First order factor in the numerator. First order factors with repeated poles. 1 by tau 1 S plus 1 whole square, whole cube, whole power n. For that what is the Bode plot? Similarly, quadratic factor. Sometimes we cannot factorize it. It will be a complex number otherwise. So we will keep it as a second order, second degree equation. That is called quadratic form. A S square plus B S plus C. Like that we will keep. For that what is the Bode plot? If I break down the given transfer function into all these factors, for each factor, what is the Bode plot? If I know, I can graphically add all the Bode plots so that I get the complete Bode plot. So for each factor, what is the Bode plot? We have to see. Next. Suppose a transfer function equal to k, only one factor is there. For that, what is the Bode plot? Bode plot means magnitude is in logarithmic scale, frequency is in logarithmic scale. Magnitude 20 log k, that's all, because g equal to k. G of j omega also equal to k, therefore 20 log k, that's all, magnitude plot. Phase plot, k, angle of k is 0 always 0. So 20 log k means that k equal to 1, 0 dB. When k equal to 1, 20 log k equal to 0 dB. When k equal to 10, 20 dB. When k equal to 0.1 means 10 power minus 1 or minus 20 log 10. So 20, minus 20. So when k equal to 0.1 means minus 20 dB. So what is the plot next? A equal to 20 log k, a positive constant, pi equal to 0 always. If k equal to 1, 0 dB always. When k angle always 0. Similarly, when k is rising between 0 and 1, a equal to 20 log k, a negative constant. If it is less than 1 means what? 0.1 if we take 10 power minus 1, therefore minus 1 dB. 0.01 means 10 power minus 2, minus 40 dB. So if it is between 0 and 1 means, less than 1 means, it will be negative value. That's all. So go next. This is a magnitude plot of k. When k equal to 10, 20 dB. When k equal to 0.1, minus 20 dB. When k equal to 1, 0 dB. K equal to 10 means 20, k equal to 0.1 means minus 20 dB. When k equal to 1 means 0 dB. Base plot always 0. Base plot is always 0. That's all. So one factor we know how to draw the plot. This is the Bode plot for g of s equal to k. That's all. Bode plot of integral factor 1 by s. The transfer function is 1 by s. 1 by s. G of s equal to 1 by s. That's all. For that we have to draw the Bode plot. So if you convert this into frequency sinusoidal transfer function, if you convert this into sinusoidal transfer function, g of j omega equal to 1 by j omega equal to minus j by omega. You multiply the numerator denominator by the j, you will get minus j by omega. What is the magnitude of that? 1 by omega, that's all. So modulus of g of j omega is 1 by omega. What is the angle for this? Minus j means minus 90. Minus 90, j means minus 90. So angle is always minus 90. Here, what is the difference between these two? This is in rectangular form, this is in polar form. So the magnitude and the angle we have to write. So write the angle for this tan inverse of imaginary part by real part. Real part is 0. Imaginary part is 1. 1 by omega. 1 by omega divided by 0 means infinity. Infinity means always 90. So minus 90. So angle is minus 90. Therefore in polar form 1 by omega angle of minus 90. So a equal to 20 log 1 by omega. The magnitude plot is 20 log in logarithmic scale, in decimal scale. Not only logarithmic scale, in decimal scale 20 log 1 by omega. So minus 20 log omega. 1 by omega means minus 20. Minus 20 log omega. The phase plot is angle of j of omega always minus 90. So what is the plot? We go for so how to draw that? So we have to substitute different values of omega. If you substitute omega equal to 1, 1 by 1 0. Log 1 equal to 0. So 0 dB. If you substitute 10, 1 by 10. 1 by 10 means what? Omega equal to 10. Go to previous slide. Omega equal to 10 means 1. So minus 20. When 10 equal to, go to next slide. When omega equal to 10 means minus 20. When omega equal to 0.1 means plus 20. Because 0.1 means 10 power minus 1 minus or minus plus. So 20 dB. So when omega equal to 0.1, 20 dB. When omega equal to 1, 0 dB. When omega equal to 10, minus 20 dB. So from that we can draw the plot. Because so many x values we have, different for that the corresponding magnitudes we have, we can draw, and the base is always minus 90. So we can draw. So this is the plot. When omega equal to 1, that is 10 power 0. 10 power 0 means 1. When omega equal to 1, what is the magnitude? 0. When omega equal to 1, 0. When omega equal to 10 power minus 1, that is 0.1, 20 dB. When omega equal to 10, minus 20 dB. Minus 20 dB. So it is a straight line passing through minus 10, plus 20, 0, minus 20, as omega varies from 0.1, 1, 10. How it is multiplied by frequency is varying by multiplied by 10, 1 decade. That we will explain later. Decade scale. The decade comes from Latin word means 10. The frequency is multiplied by 10. Omega, if you multiply the omega by 10, you will get 10 times omega. If omega equal to 1 means, if omega becomes 10, then it is multiplied by 10 times. If now omega is 10 means, if it is multiplied by 10, 100. So, if it varies from 1, 10, 100, 1000, if the frequency is varying like that, that is called 1 decade. 1 decade, multiplication of 10. here the slope at which here the line decreases at the rate of the slope decreases at the rate of, here what is the magnitude? 20 dB, here 0 dB. What is the width between from here and here? 1 decade, because here the frequency is 0.1, here frequency is 1. 1 to 0.1 is 10 times. So 1 decade. In 1 decade, the magnitude is decreased from 20 dB to 0. The change in magnitude is 20 dB. The frequency change is 1 decade. That's why decreasing, that's why minus. The magnitude is decreasing from 20 dB to 0 dB. That's why minus 20 dB per decade. That's all. Suppose if it is an octave scale, means the frequency is multiplication of 2, not 8. Multiplication of 2. The frequency is doubled means 1 octave. If omega equal to 1 means, when omega equal to 2 means 1 octave. Now omega equal to 2 means, when omega becomes 4 means 1 octave. Now omega is 10 means, when omega equal to 20 means 1 octave. 0.5 means when it becomes 1 octave. Why means in Western musical note 8 parangala in Western note. The frequency difference between two notes is double. It will be double. Frequency will be doubled. That's why totally 8 notes. That's why it is octave. Doesn't mean that the multiplication of 8. So multiply by 2. 1 octave means frequency is doubled. Suppose here, if you talk in terms of octave means, what is it will be 12 dB per octave equal to 20 dB per decade. 12 dB per octave is equal to 20 dB per decade. If you talk in terms of decade scale, 20 dB. If you talk the same in octave scale, the change in magnitude is 12 dB per octave. Mentioned about decade scale, and here the frequency is 1, here 10, that's why this is decade scale. Here the octave is mentioned here. Decade, octave is not mentioned here. So octave means here this is octave. Here it is 1, here it is 2. So this length is 1 octave. 1 octave. Here for 1 octave, the change in magnitude is 6 plus 6, 12 dB. 1 decade, the change in magnitude is 20 dB. So 20 dB per decade is equal to 12 dB per octave. Both are same. Slope, we are talking about slope. 20 dB per decade is equal to 12 dB per octave. Both are same. To explain decade and octave again, here this is 0.5, frequency is here 0.5, here 1, frequency is doubled. So this is 1 octave. Here frequency is 1, here 2, this is 1 octave. Here frequency is 1, here 10, this is 1 decade. So this is another decade. So if frequency is multiplied by 10 means 1 decade. To explain that, this slide is there. Next. Bode plot for 1 by s power n. For 1 by s, what is the slope? We got a line. The slope is minus 20 dB per decade. 1 by s. 1 by s power n. See the magnitude 1 by omega power n. What is the angle? For each 90 degree, there are n poles. That's why minus n 90. That's 2 poles means minus 2 multiplied by 90. So when to draw this, always you select the 3 frequencies: 0.1, 1, 10. 0.1, 1, 10. When we substitute omega equal to 0.1, we got 20 n dB. If 2 poles means s square means n equal to 2 means 40 dB. That's all. But when omega equal to 1, always you get 0 dB. When omega equal to 10, you get minus 20 n dB. N equal to 2 means s square means 40 dB. Minus 40. For 1 by s square we plotted. N equal to 2 it is plotted. Here it is 40 dB. When 0.1, 40 dB. When omega equal to 1, 0 dB. When omega equal to 10, minus 40 dB. The slope is minus 40 dB per decade. What is the phase plot? it is passing through minus 180 because for each 1 by s minus 90 degree, 2 1 by s therefore minus 180 degree. You got? That's all. So what is the Bode plot for 1 by s square? It is a line passing through 1 comma 0. A line passing through 1 comma 0. Omega equal to 1, magnitude equal to 0. 0 dB. Prove that it is passing through. What is the slope? Minus 40 dB per decade. Minus 40 dB per decade. Because if you take one decade, the slope is decreasing at the rate of 40 dB. Decreasing at the rate of 40 dB. Therefore, at point 1 take 40, at 1 you take 0, again at 10 you take minus 40. Draw a line that is the Bode plot for 1 by s square. Derivative factor. If the same s is in the numerator, then what is that? Instead of 1 by omega, you will get omega. G of j omega equal to omega. So, the slope is, for 1 by s slope is minus 20 dB per decade. Here, plus 20 dB per decade. Slope will increase. That is the only difference. So, you see that g of j omega equal to j omega. So, 0 plus j omega. Therefore, for this plus 90 because plus j omega. So, angle is 90 degree plus and the magnitude of this is omega angle 90. So, let us find for different frequencies when omega equal always 90, there always minus 90. For 1 by s always minus 90, for s always plus 90. Because real part is 0. Wherever the real part is 0, angle is 90. Wherever the imaginary part is 0, angle is 0. For k, what is the angle? 0. Why imaginary part is 0? For k, imaginary part is 0, that's why angle is 0. Here, real part is 0, that's why angle is 90. Plus real part, imaginary part means plus 90. Minus imaginary part means minus 90, that's all. Here, if you substitute omega equal to 0.1, a 20 log 0.1 equal to minus 20. When omega equal to 1, it is 0 dB. When omega equal to 10, it becomes 20 dB. So, the slope is increasing at the rate of 20 dB per decade. Anyhow, when omega equal to 1, it is passing through 0 dB. So, what is the plot next? You see the plot, you see, when omega equal to 1, it is passing through. When omega equal to 1, it is passing through 0 dB. When omega equal to 0.1, it is minus 20 dB. When omega equal to 10, it is passing through plus 20 dB. So, it is increasing at the rate of 20 dB per decade. 20 dB per decade. That's a Bode plot for 1 by s. If multiple zeros are there, instead of s square or s cube or s power n means s square, let us take s multiplied by s. So, omega square, 2 omega. The slope will be 40 dB per decade. 40 dB per decade. Angle will be plus 180. Okay. Now, after that, we have seen frequency domain specifications and how to draw Bode plot for each factor we have seen. Now, let us continue with it. Bode plot for derivative factor. Multiple derivative factor. If the numerator has multiple of zeros at the origin, s power n number of zeros at the origin. In that case, the magnitude is 20 log omega power n. Suppose n equal to 2 means 40 log omega is the magnitude. For phase n multiplied by 90, if it is n equal to 2 means 180. For example, if omega equal to 0.1, the magnitude becomes minus n 20 dB. For n equal to 2 means minus 40 dB. When omega equal to 1, it is 0 dB as we have seen already. For both 1 by s power n, s in the numerator, s power n in the numerator, for everything, when omega equal to 1, the magnitude plot will pass through 0 dB. Similarly, for omega equal to 10, it becomes n 20 dB or if it is n equal to 2, 40 dB. If you see the plot, in the case of 1 by s power n, it is decreasing slope, here increasing slope. Now let us see the Bode plot for the first order factor in the denominator, that is 1 by tau s plus 1 or 1 by 1 plus s tau, where tau is the time constant of the system. Here the coefficient of s is the time constant. That's why it is called time constant form. For the time constant form, if we convert this into sinusoidal transfer function, g of j omega equal to 1 by 1 plus j omega tau. If we find the magnitude, g of j omega equal to 1 by square root of 1 plus omega square t square. The magnitude is 1 by square root of 1 plus omega square t square, and the phase is tan inverse of imaginary part by real part, that is tan inverse of omega tau. Minus, why minus? Because it is in the denominator. It is in the denominator, that's why minus I. Minus tan inverse of omega tau. When a equal to g of j omega, that is 20 log, in the logarithmic scale, 20 log 1 by square root of 1 plus omega square t square. To draw this, in Bode made an approximation. Here, if omega tau is far bigger, larger than 1, then 1 can be neglected. Suppose omega tau equal to 1000 means we can neglect 1. Similarly, omega tau is far smaller. In that case, we can neglect 2. Far smaller means in that case we can neglect this and we can consider 1. Two cases, extreme cases. When it is considerable, when omega equal to 1 by tau. When omega equal to 1 by tau, the frequency equal to 1 by tau, it is considerable, it is equal to 1. 1 is equal to 1 means both are considerable quantity. If this is 0.1 means we compare with 1, this is negligible. But when omega equal to 1 by tau, the frequency equal to 1 by tau, this becomes 1. So when compare with 1, we cannot ignore that. When omega equal to 1 by tau, that frequency is called corner frequency. If you consider it as a corner frequency, or in other words, if you consider it as a midpoint between two extreme frequencies, then one side, if omega tau is far greater than 1, we can ignore 1. If omega tau is far smaller than 1, we can ignore omega square t square. But when omega equal to 1 by tau, it is considerable one, that is the midpoint, that is called corner frequency. If you draw by using this assumption, then it is called Bode plot. In other words, it is called asymptotic plots. What is asymptote? Asymptote is tangent at infinity. Asymptote means tangent at infinity. When omega is infinity, omega tau is very big number. Omega tau is very big number. In that case, 1 is negligible. So definitely, the approximation and the actual plot are same for omega is infinity. Similarly, when omega tau is negligible, very small, in that case, 1 is very big number. In that case, if you draw the plot, it is also coincides with the actual plot. In the extreme cases, it coincides with the actual plot. In other words, the approximate plot is tangent to actual plot at infinity, larger values. That's why this approximate plot is called Bode plot, a different name. It is not actual frequency response, it is approximate frequency response. To draw that approximate, so far we didn't do any approximation. For 1 by s power n, similarly s power n, k, for everything we didn't do any approximations. But here we are going to do some approximations. In that case, if omega term is negligible, we will compare with 1, we are neglecting omega square n square. Here, a equal to 20 log omega square t, omega t. A equal to, here you consider omega tau is far less than 1. Omega tau is far less than 1. Omega tau is negligible. We are approximating to 0. That's why the magnitude becomes 0. So when the frequency is very small, the magnitude is 0. We consider the next case. Omega tau is far greater than 1. For high frequency portion, this 1 is negligible. That's why minus 10. This is square root of omega square t square. Square root of 1 plus omega square t square. Square root means 1 by 2 to the power 1 by 2. If you multiply that 1 by 2, that's why this becomes 10. That's why it becomes 10. Minus 10 log omega square t square. Again, if you bring the 2 here 20, there is no need to do that. If you remove both omega square and square root, you bring omega tau. That's why you can take this step. I do not know why I put like that. Minus 20 log omega tau. In that case, 1 is negligible. That's why minus 20 log omega tau, 1 is negligible. In that case, that is high frequency range. What is the plot? When omega equal to 1 by tau, it is 0 dB. When omega equal to 10 by tau, if you substitute 10 by tau, it becomes 20 dB, minus 20 dB. So, if you consider the right hand side by neglecting 1, it starts from 0 dB, it increases at the rate of minus 20 dB per decade. So, if you plot this on similar sheet, next similar sheet, left hand side we are neglecting omega tau, that's why it is 0 dB up to the corner frequency, that is 0.2. In this case, tau equal to 5, that's why 1 by tau equal to 0.2. So, at up to 0.2 it is 0 dB. After that, its slope is minus 20 dB per decade. When omega equal to 1 by tau, that is omega equal to 0.2, omega equal to 1 by tau equal to 0.1 by 5, that is 0.2 means it is 0, again it becomes 0. After that, it is decreasing at the rate of minus 20 dB. Here we are considering omega tau only. Let us substitute omega tau, omega equal to 1 by tau. If we substitute 1 by tau, it becomes 1. So, minus 20 log 1, that is 0 dB. If we substitute 10 by t getting cancelled, minus 20 log 10, that is minus 20 dB. So, for a distance of 1 decade, 1 to 10 means 10 times a distance of 1 decade, it is decreasing at the rate of minus 20 dB per decade. Therefore, after corner frequency, the plot is decreasing at the rate of minus 20 dB per decade. Up to corner frequency, what is the plot? 0 dB. So, for a first order factor, the frequency response is, the approximate frequency response is 0 dB up to corner frequency. After that, minus 20 dB per decade. At that rate, it is decreasing. Now, let us find the difference between actual plot and the approximate plot. Approximate like this Bode plot. Error near corner frequency means what is the corner frequency value in this case? Omega equal to 1 by tau, that is corner frequency. If we substitute omega equal to 1 by tau, this is 0, this part is 0. At corner frequency, omega equal to 1 by tau, if we substitute 1 by tau, it becomes 1. So, 1 plus 1, 2, 20 log square root of 2 becomes 3 dB. So, at the corner frequency, the error is minus 3 dB. The difference between actual plot and the approximate plot is minus 3 dB. So, if you want, after drawing that approximate plot, if you want the actual plot mean, we have to do the correction of minus 3 dB at the corner frequency, that's all. So, how to do the corner frequency? Here, we have to select a point minus 3 dB below this, put a dot here. If 1 octave, if you move left hand side, the error will be minus 1 dB. If you move 1 octave to the right, the error will be again minus 1 dB. So, you can draw 3 points. 1 point is below minus 1 dB, here minus 3 dB, here minus 1 dB. If you join all these 3 dots, you will get the actual plot. So, in the MATLAB, if you give command for Bode plot, it will give actual plot, it won't give Bode plot. But if we draw, we will get the actual Bode plot, that is the approximate plot. Why it is required? Why they found this? Those days there is no computers. They have to draw the frequency response from transfer function. By looking at the transfer function, they can draw. They will factorize. For each factor, they will draw the frequency response. All will be added graphically. They will get the frequency response. After seeing the first sum, the conventional method, how to draw without doing any calculation also you will see. So, if you want the actual plot, you have to do the necessary corrections, that is minus 3 dB correction at corner frequency. To the right side, after 1 octave, you have to do minus 1 dB correction. Here also you have to do minus 1 dB correction. Here, what is the frequency? 1 octave below here means what is the frequency? The frequency should be 50% of that 1 by tau. Instead of omega tau, you are substituting 1 by tau. 50% means 0.5 by tau. 0.5 by tau. The right hand side, what is the 1 octave frequency? Here 1 by tau means, here what is the frequency? 2 by tau, that's all. If we substitute 2 by tau here, and if we substitute 0.5 by tau here, you will get that minus 1 dB and minus 1 dB. That is the necessary correction we have to do at the corner frequencies. If you do that necessary correction, you will get the exact plot. Sometimes we need that correction. Always it is not required. Unless otherwise it is required in the If it is asked in the examination, then student has to do. Otherwise, no need. And if you really want to do some design, means if the selected frequency is near corner frequency, means there is error, known error. That can be corrected by doing this necessary corrections. Otherwise, no need. For examination point of view, there is no need to do necessary corrections at corner frequencies, unless otherwise it is asked. But if you are doing some design, there you need some corrections. Actual plot is required, means you will do this necessary correction. Otherwise, no need. Now let us see the phase plot. What is the phase plot? Go to this slide. Phase plot is angle of g of j omega minus tan inverse of omega tau. Because what is the transfer function? 1 by 1 plus s tau. Or if you write in the sinusoidal transfer function, 1 by 1 plus j omega tau. Imaginary part is j omega tau. So angle is tan inverse of minus. Why minus? It is denominator. That's why minus tan inverse of omega tau by 1. So omega tau. As omega tends to 0, this becomes 0. As omega tends to infinity, it becomes 90. So phase shift varies from 0 to minus 90. That's all. That's why the phase shift is varies from 0 to 90. Minus 90. Varies from 0 to minus 90. At corner frequency, definitely it is 45. Because 2. When omega equal to 1 by tau, it becomes 2. So that's why you will get 1. This is at 1 decade, 1 octave below corner frequency, 1 octave above corner frequency. What we substituted? I said 0.5 by t, or you can substitute 1 by 2t. If you square it, 1 by 4t square. So similarly here, to the right side if you move, here we substitute omega equal to 2 by tau. That is 4 by t square is substituted, and again it is approximately equal to minus 1 dB. So, to the right you have to do minus 1 dB correction, the left side you have to do minus 1 dB correction to get the actual plot. And what we plotted is approximate plot or asymptotic plot or Bode plot. This is for multiple factors. If it is m means phase shift will be multiplied by m. Similarly, magnitude is to the power m times what we got in the previous plot. That's all. Next. Here, if it is m equal to 2 means we are getting m equal to 2 means we are getting 40 dB. M equal to 3 means we will get 60 dB. Then 60 dB per decade. 60 dB per decade. This is mistake. It must be m equal to 3 and here m equal to 2 and 3 means 60. For m equal to 1 means what we are getting? 20. So m equal to 2 means minus 40. This must be 1 and this must be 2. Here also m equal to 1 and 2. Since it varies from 0 to 180, this varies from 0 to 90. M must be 1. This is okay, next. If we have a factor in the numerator, means the plot will be like this. Up to corner frequency 0, after that slope will be positive. That's all. Slope will be positive. It has repeated zeros. The first order factor in the numerator. If m equal to 1, up to corner frequency. What is corner frequency? Omega equal to 1 by tau. That is the corner frequency. Up to corner frequency, the magnitude is 0. After that, it increases at the rate of 20 dB per decade. So the plot will be like this. Then it will be like that. When m equal to 1. When m equal to 2, up to corner frequency it is 0. After that, it increases at the rate of minus 40 dB per decade. It increases at the rate of minus 40 dB per decade. Yes, when m equal to 1, it is 20 dB per decade. It increases at 20 dB per decade. When m equal to 2, it increases at the rate of 40 dB per decade. This is actual plot. This is approximate plot or asymptotic plot. This is actual plot. This is a phase. Phase varies from 0 to 90 for m equal to 1. For m equal to 2, it varies from actually it is m equal to 0 to 180 means m equal to 2. Yes, here it is correct. 0 to 180 means m equal to 2. 0 to 270. Yes, it goes to 270. M equal to 3 means it varies from 0 to 270. Here, m equal to 2 means the slope is m equal to 3 means 60 dB per decade, but positive slope. Positive slope if it is in the numerator. Quadratic factor. So, what is the asymptotic plot or Bode plot for a quadratic factor? The second order transfer function is given in time constant form. Already we have seen the time second order transfer function in natural frequency form. Already we have seen s square plus 2 zeta omega n s plus omega n square in the denominator, that is natural frequency form. Here it is given in time constant form, t square s square plus 2 zeta tau s plus 1, time constant form. For that, if you find the sinusoidal transfer function, we got this. If you find the magnitude, what is the real part? 1 minus omega square t square, that is the real part, whole square, plus what is the imaginary part? 2 zeta omega tau is the imaginary part, 4 times zeta square omega square t square, that is imaginary part, square root, that is the magnitude. Phase is tan inverse of 2 zeta omega tau divided by the real part, 1 minus omega square t square. So we got the phase also. Now we have to do the approximate plot for this. For that, if omega tau is far greater than, then here omega square tau square is to the power 4. Already omega square t square is negligible, means omega square t square to the whole square means to the power 4 also negligible. This is already omega square t square multiplied by zeta. Zeta is less than 1 means further it is negligible. Then what? Omega tau is negligible means omega is less than the corner frequency means omega tau is negligible. In that case we get 1 only, so 0 dB. After corner frequency, this go to next, that approximation we use. Here, when omega tau is far less than 1, omega square t square, 4 zeta square omega, both are negligible, that's why it becomes 20 log 1, 0 dB. When omega t is far greater than, then 1 minus omega square t square is 1 is negligible. That's why it becomes omega square t square whole square, that is omega square to omega power 4 t power 4. When compared with omega power 4 t power 4 to zeta, omega square t square is negligible. 4 zeta square omega square t square is negligible when compared with omega power 4 t power 4. That's why we are neglecting this one as well as this, and it becomes square root of omega square t square. Square root of omega power 4 t power 4, that is equal to 1 by omega square t square. How we are taking the approximation? We are neglecting both 1 as well as this one is neglected when compared with omega power 4 t power 4. So we got this expression. A is approximately equal to minus 20 log omega square t square or minus 40 log omega t. For first order factor we got minus 20 dB per decade. Here we got minus 40 dB per decade. That is the only difference. Up to corner frequency 0 dB, after corner frequency minus 40 dB per decade. So when omega, now let us to draw this we need this. To draw that we need this. For 1 decade, what is the difference we are finding? When omega equal to 1 by tau, that is omega t equal to 1, we substitute here 0 dB. When omega equal to 10 by t, 1 decade after, then log tau we will get, therefore minus 40 dB we are getting. So in a decade of distance from corner frequency, the magnitude is minus 40 dB. Therefore, the slope is minus 40 dB per decade. So we got the plot like this. This is the approximate plot. Up to corner frequency 0 dB. After that, it decreasing at the rate of minus 40 dB per decade. If you see here, actual plot it is different because as zeta decreases, there will be a resonant frequency. Resonant frequency is that. That's why when zeta equal to 0, it has a very high magnitude, approximately equal to infinity. And as zeta further increases, it is for 0 very high magnitude. If you further increase the zeta, it decreases. When about 0.7, it almost coincides with the real plot, actual plot. If you further increase that zeta, its magnitude monotonically decreases. So, if it is a second order system, at corner frequency, the difference error is function of zeta. If zeta is very small, error will be very large. If zeta is very big, error will be small. So, inversely proportional to zeta. So, for phase plot also, it is also varying based on the zeta. So, for second order system, we have to do the necessary corrections at the corner frequency if we do any design near corner frequency, otherwise no need. Suppose you are doing a correction, you are doing a design at this frequency means no need to do this necessary correction here. Similarly, if you do any design at this frequency means no need to do the correction here. If you do any design near corner frequency, you have to do the necessary corrections. Otherwise, no need. For examination point of view, no need. They have to draw this. That's all. For examination point of view, the student has to draw the approximate plot, unless otherwise draw the exact plot is asked. Otherwise, no need to draw. So here the error between actual plot, this is the actual expression. If we ignore omega square t square is ignored, then it is 0. We assume that's why log 20 log 1. What is the error if you see? It is about next slide. It is about minus 60. It is not mentioned here. About 60 dB, but it is function of zeta again. It is about function of zeta. If it is zeta equal to 1, then the error will be about 60. Next, the error expression is function of zeta and omega. We have to substitute the value for zeta as well as omega to get the error. This is the actual plot expression. This is the approximate plot expression when omega t is far greater than quantum frequency. So if you substitute omega and zeta, you get the error. Next, this is the error plot. The plot between frequency, that is normalized frequency, and error. When the zeta is very small, error is very large. Next. About point, go to previous slide. About 0.7, there is no much error. See that this is 0.8, this is 0.5, about 0.7 error, this is 0.6, 0.5, 0.8, about 0.6 and 0.7 error is very small. The same thing for a numerator factor. If you see the numerator factor, the plot will be up to quantum frequency 0. After that, it increases at the rate of 40 dB per decade. It increases at the rate of 40 dB per. So far, we have seen for individual factors. Now, how to draw a Bode plot for given transfer function. For that, a step-by-step procedure is there. The first step is convert the given transfer function into time constant form. Because the Bode plot gain k plays important role. For k, we got on horizontal line. If k equal to 1, it is passing through 0 dB. K equal to 10, it is passing through 20 dB. K equal to 0.1, it is passing through minus 20 dB. We have seen. So k plays very important role. Means k value must be correct. To make the k value correct, it should be in the transfer function model. So it should be in transfer function model. That's why it should be converted in transfer function model to make the k value correct. That is the first step. Second step, find sinusoidal transfer function replacing by s by j omega. After that, prepare a table. The first is factor. So we are factorizing the given transfer function into many factors. Each factor we are taking. Then for that each factor we have to find the quantum frequency. Quantum frequency is nothing but 1 by tau. When omega tau becomes 1, that is the quantum frequency. When omega tau becomes 1, when omega equal to 1 by tau. So the quantum frequency is 1 by tau. So we have to write the quantum frequency here for each factor. Slope contributed by each factor. If it is 1 by s, what is the slope contributed? Minus 20 dB per decade. For entire span, minus infinity to plus infinity, the slope is minus 20 dB, minus 20 dB per decade for 1 by s. Suppose s in the numerator, the slope is plus 20 dB per decade from minus infinity to plus infinity. But for first order factor, up to quantum frequency 0 dB, after that minus 20 dB per decade, first order factor in the numerator means up to quantum frequency it is 0 dB, after that plus 20 dB per decade. So up to quantum frequency there is no slope contribution if it is first order factor or second order factor. That's why we have to write the factors in ascending order. If you write in the ascending order, then if you add the slope contributed by each factor, we will say that if it is first order factor in the denominator means slope contributed minus 20 dB, we simply say, but it is not minus 20 dB. After quantum frequency only it is minus 20 dB. So automatically if you write this in ascending order, automatically the error will be adjusted. We are considering only after quantum frequency. That's why if you add minus 20 dB, there won't be error. There won't be any error. That's why it is very important to write all factors in ascending order of quantum frequency. Ascending order of quantum frequency. That is very important. Find the slope contributed by each factor. Here, first order factor or 1 by s we need not bother because we are writing in the ascending order of quantum frequency. So we are considering only after the quantum frequency. So automatically minus 20 dB per decade for denominator factor, for numerator factor automatically plus 20 dB in the case of first order. So then the fifth point is Find the net slope by adding all slopes. Each factor contributes some factor. It will be added here. You will get a net slope. Next. Find the coordinates. Now we have to find the coordinates. So here we know all x coordinates. Already we know. How? Because here the given transfer function is factored like that. K is separated. 1 by s is separated. 1 by tau s plus 1 is separated. 1 by tau square s plus 2 zeta tau s plus 1, that is separated. For each factor, the slope contribution is for k no slope only horizontal line with 20 log k, that's all. For 1 by s minus 20 dB for the entire span of frequencies. For first order factor after common frequency minus 20 dB. For second order factor after common frequency minus 40 dB per decade. So we know common frequencies means we know the x coordinates. Wherever it is changing the slope means we know the x coordinates. Only thing is we have to find y coordinate. Y coordinate means we know the equation of straight line. We know the slope of the line, if we know means we can write the equation of the straight line. We know slope. What is the slope? If it is first order factor minus 20 dB per decade. Second order factor minus 40 dB per factor. If it is 1 by s minus 20 dB per decade. So we know the slope of a line. If we know one coordinate, we can find the other coordinate. So in that way, let us find the coordinate, other coordinate, if we know one coordinate. For example, I am connecting two corner frequencies, omega 1 and omega 2. If I know both values at omega 1 means, I can find the coordinate of omega 2. From omega 1 to omega 2, the slope is minus 20 dB per decade. Let us assume. So the slope is minus 20 dB per decade. The line equation is y2 minus y1 equal to m, that is slope multiplied by x2 minus x1. That's all. x2 minus x1, that is geometry. From that we can write a line equation. Here the x-axis is in logarithmic scale. That's why log x2 minus log x1. That's why we wrote like this. But y2 minus y1 equal to net slope. We know y2 minus y1 can be written as log omega 2 by omega 1. If you bring this omega 1 to the right hand side, y2 can be found. So if you know x1, y1, we can, and if you know x2, we can find y2. So by using this formula, we can find the coordinates. In that way, we can draw the Bode plot. Next, we have to select the scale for the semi-log sheet. All Bode plots will start at point 1 because for 1 by s it is passing through 0. Omega equal to 1, it is magnitude is 0 dB. For numerator s, it is passing through 0 dB. Its magnitude is 0 dB at omega equal to 1. So always the Bode plot should include omega equal to 1. So omega equal to 1 should be included means that's why we have to start the Bode plot from point 1. All Bode plots, if you see, it starts from point 1 omega equal to point 1. Unless otherwise any corner frequency is less than 0.1, then only we have to start from point. Suppose any corner frequency is less than 0.1 but greater than 0.01 means we have to start from 0.01. Suppose any corner frequency is less than 0.01 means, but it is corner frequency is greater than 0.01 means we have to start from 0.01. Otherwise, always start the Bode plot x-axis with 0.1. That's all. Always start the x-axis with 0.1 radians per second. So always you have to start with 0.1 radians per second. If any corner frequency is less than 0.1 radians per second, then we have to start either from 0.01 or 0.001 or 0.001, depends. Otherwise, you start always from 0.01. Then next, y-axis you can select as you wish. It can be taken from minus 40 to plus 40. That is sufficient. Sometimes if it requires more, we can select accordingly. So y-axis, the corner frequencies and net slopes and corner frequencies as entered in the table can be used to draw the asymptotic magnitude plot. So corner frequencies are x coordinates. Y coordinates can be obtained from the formula y2 equal to net slope multiplied by log omega 2 by omega 1 plus y1. From that formula we can find y coordinates. Then we can draw the magnitude plot. Phase plot, we know the range of frequencies. Substitute in the phase formula, find the angles and draw. That's all. Now let us see one sum. Go to the next. This is asked in May 2014. Sketch the Bode plot showing magnitude in decibels and phase angle in degrees as follows. He mentioned Bode plot, but he is making confusion showing magnitude in decibels, phase in angle in degrees as function of log frequency for the transfer function. Sometimes they will miss the Bode plot and showing that magnitude in decibels and angles in degrees for an approximate plot. Without telling Bode plot, they may tell like that. So G of S equal to 75, 1 plus 0.2s divided by S multiplied by S square plus 16s plus 100. What is the type of transfer function? Whether neither it is in transfer function model nor in natural frequency. In the numerator it is in time constant form. In the numerator it is in time constant form. In the denominator it is in natural frequency form. So everything should be in time constant form. Already we have seen that to make the k correct. Otherwise you will get wrong result. If you do the necessary corrections here, divide the denominator by 100. You will get this becomes 1, this becomes 0.16 and this becomes 0.001 s square. So this becomes in time constant form. Here also it is in time constant form. So if you divide by 100, this 75 becomes 0.75. So this is the first step we have to do is convert the given transfer function into time constant form. That is first step is over. The second step is we have to replace s by j omega transfer function, sinusoidal transfer function we have to find. That is also obtained replacing s by j omega. To find the corner frequency, slope contributed by each factor and the net slope we have to find. We have to fill the table. For that, we have to consider each factor separately. The first factor we are considering is 1 by s or 1 by j omega. Here, while drawing the Bode plot, this constant factor always will be included with 1 by s or s term. So 0.75 divided by j omega is combined together because why they are combined? Because 0.7 is also for minus infinity to plus infinity. 1 by j omega also from minus infinity to plus infinity. There is no corner frequency at all. That's why they can be combined. And they can be easily calculated by 20 log formula. That's why they are combined. For 0.75 also the formula is 20 log k. For 1 by omega also the formula is 20 log 1 by omega. That's why they are combined. For the factor 0.75 by j omega, there is no corner frequency. The table, this is the first. If there is no corner frequency, means that is the first factor. The second factor which has what is the corner frequency for this? Tau equal to 0.2. What is the corner frequency? Corner frequency equal to 1 by tau. Corner frequency is 1 by tau. 1 by point equal to 5. Therefore, for this factor, for the numerator factor, the corner frequency is 1 by 0.2, that is 5. For this, what is the corner frequency? Tau is, here you cannot find tau. From this you can square root, it is tau square. Here it is tau square. Here it is 2 zeta tau. That's why from here we cannot find tau. From here if you take the square root, you will get tau. So if you take the square root, the corner frequency is for this third, for the factor, it is written here. Sorry, we didn't see that. Here the corner frequency is 10. It is written here. So if you write this in ascending order, next slide. Ascending order, there is no corner frequency for the first factor 0.75 by j omega. There is no corner frequency. Slope contributed from minus infinity to plus infinity minus 20 dB, and net slope is minus 20 dB. The coordinates are 0.1 and 17.5. What next slide? How we found the substitute? Because already I said for k also the formula is 20 log k. For 1 by omega also the formula is 20 log k. 1 by omega. So directly substitute in that formula 20 log 0.75 by j omega, that is 0.75 by omega. The substitute we got 17.5. When omega equal to 0.1, why I substituted 0.1? We are starting the Bode plot from 0.1, omega equal to 0.1. That's why we substituted 0.1. We got 17.5. Therefore, coordinate is 0.1, 17.5. Coordinate is 0.1, 17.5. What is the next corner frequency? 5. Next corner frequency is 5. What is the factor? Factor is in the numerator. What is the slope contributed by this? 20 dB per decade after corner frequency. After omega equal to 5, the slope is plus 20 dB per decade because it is a numerator. Positive slope. Already the slope is minus 20, net slope. Now contribution is plus 20. If we add these two, we get 0. That's all. Now we have to find the coordinates at this corner frequency. At 5, we have to find the coordinate. Up to 5, what is the slope? from 5 0 dB. From 5 0 dB. Because after corner frequency only we are getting slope minus 20 dB. So net slope means you have to substitute the previous value. That is the crucial point. Net slope means you have to substitute the previous value. While calculating coordinate, you have to use this 20 because up to this point there is no slope contributed by this. There is no slope contributed by this factor up to corner frequency. Corner frequency is 5. Up to 5 it does not contribute any slope. So whatever slope is contributed by previous factors only. The slope is minus 20. Therefore, the formula is y2 equal to net slope is minus 20 log omega 2 is 5, omega 1 is 0.1, 5 divided by 0.1 plus y1 is 17.5. y1 is 17.5. y1 is 17.5, omega 1 is 0.1, omega 2 is 5, net slope is up to omega 2 is minus 20. What is y2? y2 equal to minus 20. Slope log 5 by 0.1, omega 2 by omega 1 plus 17.5 minus 16.47. Coordinate at 5 is 5 comma minus 16.47. These are the coordinates. Next we have to find next factor is quadratic factor. Here the corner frequency is 10. The slope contributed from 10 is minus 40. So here net slope earlier is 0. If you add minus 40, you get again minus 40. If you add this, if you have to find the coordinate. When finding coordinate at 10, up to 10 there is no contribution by this factor. So we have to consider this slope. Omega 1 is 5, omega 2 is 10, net slope is 0, y1 is minus 16.47, therefore y2 equal to 16.47. Go to previous table. I think the table is wrongly entered. 16 point instead of 16.47 it is entered as 56.47. Minus 14.47. It must be minus 16.47. Minus 16.47. Now we have to find the slope at the coordinate at 100. Another 1 decade away. 1 decade away we have to find. Otherwise we cannot draw the line after 100. How we can find? This is after corner frequency. This 100 is after the corner frequency of 10. That's why slope is minus 40. That's why slope is minus 40. To find the coordinate at omega equal to 100, y1 equal to minus 16.47, omega 1 equal to 10, omega 2 equal to 100, net slope is minus 40. If we substitute here, we will get minus 56.47. So that's all. We got all coordinates. Join all coordinates, we got Bode plot. Join all coordinates, we get a Bode plot. How to draw this? What is the phase angle of 0.75 by j omega? For all 90 degree, minus 90 degree. Only imaginary part. If you, the 2 in the denominator, minus 90, already we know. For this numerator factor, positive values, tan inverse of 0.2 omega, we got angles. So, for quadratic factor, in imaginary part by real part, here, if you find after corner frequency, we had add 180 degree. So, in the cancelling, you will get 0 to 90 degree only for because of quadrant problem. Because of quadrant problem, we have to add 180 degree while calculating the angle after corner frequency. Here, corner frequency up to 10. 10 is the corner frequency for quadratic factor. 50 is after corner frequency. That's why we have to add 180. We have to add 180. How to calculate the gain margin and phase margin? Gain margin and phase margin. Already we have seen that in a polar plot. We have already seen that if any transfer function, if you increase k, the polar plot will magnify. The polar plot will magnify, there won't be any change in phase. That's why as k increases, it will encircle that minus 1, so the system becomes unstable. That's why the margin is very important. We cannot increase beyond minus 1. So the margin we can count how much gain we have to increase so that the polar plot is passing through minus 1. That already we have seen in the morning, gain margin definition. For phase margin, if we introduce phase change only in that plot, without changing magnitude, the point is moving to that minus 1. We have seen that. That is in polar plot. Here, We have to consider the same thing. Where we have seen that gain crossover frequency, where it crosses magnitude 1, that is gain crossover frequency. Here log 1 equal to 0. Therefore, at 0 dB, what is the frequency we have to see? This is the frequency. What is the frequency? This is 1. So 0.9, 0.8, 0.7, 0.6, 0.5. 0.5 is the gain crossover frequency because at 0.5 it crosses 0 dB. That is magnitude 1. Let's say this is gain crossover frequency. What is the phase crossover frequency? Where it crosses 180. It crosses 180 here. The phase plot is crossing 180 here. The frequency at this point, that is 1, this is 2, maybe 1.5. So 1.5, this is the phase crossover frequency. So if you to find the gain margin, we have to consider phase crossover frequency. To find phase margin, we have to consider gain crossover frequency. At the phase of crossover frequency, we have to see the magnitude. What is the magnitude? Minus 15.57. The magnitude is minus 15.57. At 180, that is at phase crossover frequency, the magnitude is minus 15.17. Now the magnitude is 15.17. To make 0, how much I can add? 15.17. Therefore, gain margin is 15.17. System is stable. System is stable. If it is negative, gain margin is positive. Because I can add that much gain so that the system becomes unstable. So that the system becomes the verge of unstable. Verge of instability. That's why the gain margin is 15.57. What is the phase margin? At 0 dB, bring here, this is the gain crossover frequency. At the gain crossover frequency, what is the phase angle? 120 minus 120.5. Therefore, phase margin is 180 minus 120. How much? 59.5. 59.5. The phase margin is 59.5. That is also wrong. 60.5. 59.5. This is the phase margin. Phase margin is 180 minus angle at gain crossover frequency. So we got 59.5 degrees. We got. You see that where is the phase crossover frequency? Phase is crossed here at 180. This is the 180 crosses here. What is the magnitude at that point? The magnitude is plus 10. Magnitude is plus 10. So magnitude plus 10 means it is already positive. Unstable system. The system is unstable. Now margin is, we have to make the system stable, we have to decrease the gain. What is the phase margin? We have to see the gain crossover frequency. Gain it crosses here. The magnitude 0 dB it crosses here. At that point, what is the phase angle? Phase angle is minus 200. 180 minus 200. We got the minus of minus. What is that? 180 minus 200 minus 20. So again unstable system. We got negative value, unstable system. We have to improve the system by decreasing K. What is the difference between the two systems? If we see, the previous system gain is 1, K equal to 1. K equal to 1. But the denominator is same transfer function. The next system, the gain is 15. If I increase the gain to 15, the system becomes unstable. That's why you cannot increase gain beyond a certain value. If you increase gain beyond a certain value, the system becomes unstable. The system becomes unstable. What is phase crossover? Already explained. What is phase crossover? What is the phase crossover frequency? Gain crossover and gain crossover frequency. Phase crossover is the point at which the phase plot crosses 180. Phase crossover frequency is frequency at which the phase plot crosses 180. Similarly, gain crossover frequency is frequency at which the gain crosses 0 dB. That is 1 magnitude, linear scale magnitude 1, where it crosses 1. Route array. By using route array, we can find how many roots are on the right hand side. How many roots are on the right hand side of it. Any poles on the right hand side of a split system is unstable. In those days, there is no MATLAB. We cannot find the roots of any system. For that, they found the method to find how many roots are on the right hand side. This route array will give you how many roots are on the right hand side, as well as it gives the value for maximum K. The value of K at which the poles are exactly on the JPEG axis, it will give. So for that, we have to take the S over 1 row. You have to take s power 1 rho to equal to 0. 0 is both neither positive nor negative. So it can be included in the positive as well as negative. So if there is no sign change in the first column, the system is stable. If any 0 is there, the poles are exactly on the geometric axis. That's why we are making this equal to 0. If we make this equal to 0, 6 minus k equal to 0 means k equal to 6. Substitute that value here. If we take this row, 3s square plus 6 equal to 0 because k equal to 6. From that we can find the frequency of oscillation. We can find the frequency of oscillation because if the poles are exactly on the geometric axis, it continuously oscillates with constant amplitude. Therefore, the range of k must be 0 to less than 6, not 6. If it is 6 means continuously oscillating. Therefore, the system will be stable if k value lies in between 0 and 6. How they put the 0? Because here the smallest positive value is 0. That's why it should be above 0 but below 6, then system is stable. The same can be found from Bode. So in Bode, 20 nor k equal to, what is the gain margin? 15.57. We have seen gain margin is 15.57. 20 nor k equal to 15.57. K equal to 6. So if you increase the gain by 6, the system becomes in the range of instability. It will exhibit sustained oscillation. After that it becomes unstable. So from Bode plot also we can find k max. That's why both are compared. Gain adjustment using Bode plot. Already we know that we can find the k max. How to find the k max by using Bode plot already we have seen. Take gain margin, 20 log k equal to gain margin. From that we can find the k max value. I want to adjust gain in such a way that I want this much gain margin. For that, how to adjust k, that can be done. So suppose I want a particular gain margin means what is 20 log k equal to gain margin, already we have seen formula. So the required gain margin is a. Therefore, what is the value of k? Easily found. 20 log k equal to the gain margin. Therefore, what is the value of k? For that, you have to draw the Bode plot with k equal to 1. Otherwise, you will get wrong result. You have to draw the Bode plot. Suppose they gave some k value. In that sum means you want to find the value of k for which the system is this much gain margin. For that, you have to find k means you have to draw the Bode plot with k equal to 1. Then you will get the value of k for which it will satisfy the given gain margin. That's all. The only thing is 20 log k equal to a. Exact plots already explained. Asymptotic plot and actual plots is how to make asymptotic plot into exact plot. For that we have to do necessary corrections at the corner frequency and 1 octave below and 1 octave above. We have to do necessary correction. If it is first order, necessary correction, from that we can do exact plot. Here one question is asked, hence obtain the exact plot by doing necessary corrections at the corner frequencies. So at the corner frequency, if it is first order factor, do 3 dB correction at corner frequency. If it is denominator factor, minus 3 dB. If it is numerator factor, plus 3 dB correction. Similarly, at 1 octave below and above, you have to do 1 dB corrections. Then you will get the exact plots. So draw the Bode plot of system GFS, hence obtain the exact plot by doing necessary correction at corner frequencies. Find the gain margin and phase margin. Find the value of k for the phase margin equal to 20 degree. Find the value of k for the phase margin equal to 20 degree. So we have to adjust k to get the required phase margin. The transfer function already in time constant form. That's why no need to convert this in time constant form. Already it is in time constant form. Converting this into sinusoidal transfer function. The third is we are finding the corner frequencies and factors. The corner 1 by s is one factor, 1 by s plus 1 is another factor. Here the corner frequency is 1 by s plus 1. 1 by 1 plus 0.4 s plus 0.2 s square means tau square equal to 0.2. Square root of 0.2 is so 2.3 is higher. That's why we are writing this in ascending order of corner frequencies. Slope contributed by this for minus infinity to plus infinity, it contributes minus 20. This is after corner frequency of 1, it contributes minus 20. This is after corner frequency of 2.3, it contributes minus 40. Therefore, the net slope is here minus 20, here minus 40, here minus 80. We have to find the coordinates. The first coordinate, how we will find for 1 by s, we have to find the corner frequency. Next, at omega equal to 0.1, 20 log 1 by s, that is 1 by omega. If you substitute, we are getting 0.1, not 20. Already we know 1 by s always starts at 20 dB. So we got the coordinates. For this, no need to use the formula. Here we have substitute just 20 in the magnitude. That's all. Now we have to use the formula at omega equal to 1. Y1 equal to how much? Y2 we have to find. Y2 equal to here 20. Y1 is 20. Y1 is 20. Y2 equal to, it must be Y2. Y2 equal to minus 20. That is slope. The previous slope is minus 20 log. The new corner frequency is 1. Previous corner frequency is 0.1. 1 by 0.1, that is 10. So minus 20 plus 20 0 dB. So coordinates are 1, 0. The next, at omega equal to 2.3, the previous slope is minus 40. Previous slope is minus 40. Log 2.3. Previous corner frequency is 1. Present corner frequency is 2.2. Omega 2 by omega 1. Plus previous y1 is 0. We add, you will get minus 14. Therefore, coordinate is 2.3, minus 14.5. At omega equal to 23. 1 decade away means 10 times 23. Y23 equal to minus 80. 80 is previous. After corner frequency of 2.3, it is 80 slope. Minus 80 log omega 2 by omega 1, that is 23 by 2.3 minus the y1 value minus 14.5, we got 94.5. So the coordinate is 23, minus 94.5. Here, this is 0. At this is the gain crossover frequency. The phase angle at this point is minus 150. Minus 150 means 180 minus 150. So phase margin is 30. Gain margin is where it crosses 180, here it crosses 180. The magnitude at this point is minus 5.5. Am I correct? Whether it is minus 5.5, therefore gain margin is 5.5. Now we have to, that's all. Find the gain margin and phase margin is one question. Gain margin is 5.5, phase margin is 30 because 180 minus 150 equal to 30. That, now the second part of the question is find the value of K so that phase margin is 20 degree. Things are made based on the formula. This table is what previous. This table is based on the formula. For each factor, error is separately. Next, gain margin, phase margin. What previous is? Gain margin is 5.5. Phase margin is 30. What we have seen in the plot. Next, find the required gain margin is 10 dB. Existing gain margin is 5.5. The question is find the value of K so that the required gain margin is 10 dB. But what is the value there? 5.5 only. I have to increase the gain margin to 10. So how much gain margin is short? 4.5. So 20 log K equal to minus 4.5. 5.5. It is not sufficient for me. I need 10. The magnitude at phase crossover frequency must be 10, but it is 5.5 only. Additional, how much required? 4.5. How much? So I have to pull down. Magnitude plot has to be pulled down. How much? By 4.5. Therefore, 20 log K equal to minus 4.5. I have to decrease. Then only the phase margin will, gain margin will increase. So 20 log K equal to minus 4.5. Therefore, K equal to 0.596. 0.596. That's all. That is called adjusting K for required gain margin. Required gain margin is 10. Present gain margin is 5.5. The deficit is 4.5. Therefore, 20 log K equal to minus 4.5. You have to pull the Bode plot down. Down means minus 4.5. If you pull down, then only there will be increase in gain margin. So if the negative increases, then only positive gain margin will get. That's why we have to pull down. Pull down, that's why minus 4.5. Now we come here. The existing gain crossover is 0.8. Required gain crossover is 1.2. Find the value of K so that the gain crossover frequency is 1.2 radians per. Question may be like this. The existing gain crossover frequency is 8. The question is, I want to find the value of K so that new gain crossover frequency is 1.2. So now what we have to do? At 1.2, the gain is minus 5 dB. Right? At 1.2, the gain is minus 5 dB. So make it equal to 0. to make it equal to 0, how much we have to add? Minus 5.5 to 0, we have to add plus 5. So 20 log k equal to plus 5, therefore k equal to 1.78. 1.778. So we have to use some logic here. Here y is equal to minus 4.5. We have to increase the gain margin, that's why minus 4.5. Here, at 1.2, the gain is minus 5. To make it 0, we have to push up. Then only it will go to 0. To make this equal to 0, we have to add 5 dB gain. That's why 20 log k equal to 5 dB. Therefore, k equal to 1.778. If you put a gain of 1.778, the gain crossover frequency becomes 1.2 radians per second. Required phase margin is 45. What is the present phase margin? 30. So I have to adjust k value so that it meets the required phase margin. So at 0 dB, we need 45 degree we require. What must be the angle? If I want phase margin of 45 means, what should be the angle at the point? 180 minus some angle should be 45. Plus 45. So 180 minus 135 equal to 45. So I need an angle of 135. I need an angle of 135. To make that angle 135, what is the magnitude at 135 we have to see. We have to see what is the magnitude at minus 135. So at minus 135, this is 135. 135 is the required. So at 135, the magnitude is, what is that? The magnitude is 4 dB. Minus 4 dB or plus 4 dB? Above. So plus 4 dB. So we have to, so 4 dB. At minus 135 phase margin, it is 4 dB, but it must be 0 dB. At 0 dB only we will see the phase margin. So to make this 0 dB, so we have to add minus 4 dB. Minus 4 dB. Therefore, 20 log k equal to minus 4 dB. So therefore, k equal to 0.63. 0.63. So you will see all these 5 once again. It definitely will confuse you. Definitely will confuse you. Once again we will see. Then we will get a clear idea. Go to A. Now we are in D. Previous. A. Find the phase margin and gain margin. That you know. You will find gain crossover frequency, phase crossover frequency, gain margin, phase margin. So that way you know very clear. No problem. Second part. Next. Previous. Required gain margin is 10. But what is the present gain margin? 5.5. 5.5 means in the plot minus 5.5. 5.5 means in the plot it is minus 5.5. But I want a 10 means it must, in the plot it must be minus 10. It must be minus 10. It must be minus 10 means we have to push down the Bode plot. Then only it will be minus 10. Push down. You have to push down means you have to decrease the gain. If you decrease the gain, then Bode plot will decrease. Already you know 20 log k. K is 10, 20 dB. K equal to 0.1, it is minus 20 dB. So if you increase k, the Bode plot goes up. So you have to push down means, how much you have to push down? Minus 4.5. Because already it is minus 5.5, but we need minus 10. So how much I have to push down? Minus 4.5. So it must be minus. So 20 log k equal to minus 4.5. That's why 20 log k equal to minus 4.5. 20 log k equal to minus 4.5. Suppose the question is this way, then you will get positive. Now it is 5.5. I want 4.5 only. The Bode plot has to go upward. Up to positive. So 4.5 minus 5.5 minus 4.5, 1. So 20 log k equal to 1. 20 log k equal to 1. So k equal to this 10 power 1 by 2. Like that you have to. You understand that? Whether you have to push up or push down, you have to consider. Push down means minus, push up means plus. Next question. The existing gain crossover frequency is 0.8 radians per second. That is not at all required. That is not at all. If required and the existing same means you can leave it. No adjustment is required. That's why it is given. It is not simply given. Both are same means no need adjustment. But existing gain crossover frequency is 0.8 radians. 0.8 radians. But required gain crossover frequency is 1.2 radians per second. So different, that's why I have to do something. Gain crossover frequency means what? What is gain crossover frequency? Where the magnitude plot crosses 0 dB. Where the magnitude plot crosses 0 dB. So it crosses at different point, different frequency. That's why 0.8. It crosses 0 dB at 0.8 radians, not at 1.2. Now it should cross at 1.2 radians per second. Now what I will do, at 1.2 radians per second, what is the gain I will see? What is the gain I will see? It is minus 5 dB. It is minus 5 dB. It must be 0. Then it is gain crossover frequency. How I can make minus 5 dB into 0 dB? It must be plus 5 dB. So 20 log k equal to 5 dB. Suppose it is like this. At omega equal to 1.2 radians per second, it is plus 5 dB. What you have to do? You have to push down. Then 20 log k equal to minus 5. So you have to think and apply. You cannot remember a formula and will not work out for this. You have to think and apply. What we have to do? So at 1.2 it must be 0 dB, but here minus 5 dB. If you add 5 dB, it becomes 0. So 5 dB. 20 log k equal to 5 dB. Therefore k equal to 1.78. That's all. Next. Sometimes they will ask the purpose of Bode plot is to find the mathematical model. Experimental way we can find the mathematical model. If we know the frequency response, the given actual frequency response is converted into asymptotic Bode plot. It can be done. We have to draw asymptotes on the plot so that we will get the asymptotic plot. If we draw the tangents on that actual plot, we will get asymptotic plot, that is called Bode plot. If we know the Bode plot, this is the Bode plot. The actual plot may be like this. It will be like this. Here it may be like this. So I joined tangents, I draw the tangents and I got the asymptotic plot. From this I can find the mathematical model. So to find mathematical model, we need time constants. That's all. Time constants, and already we know that it is initially their slope means definitely it is 1 by s only. If it is 1 by s means there will be a decrease in slope, minus 20 dB. Therefore, a 1 by s is there. But this 1 by s always goes through omega equal to 1. But it is not going through omega equal to 1. It is not going through omega equal to 1. If we extend this, already this is 4. This will cross here. So it is not going through 1. Therefore, some k is there. That k we have to find. We have to find that k. Now we have to find k. But already we find that 1 by s is there. 1 by s is there. Next, what is the slope? Minus 20 dB is changed to minus 40 dB at this corner frequency at omega 1. So at this corner frequency, your first order factor is there. So that's why this minus 20 dB becomes minus 40 dB. So here, this minus 40 dB becomes minus 20 dB. Therefore, some numerator first order factor is there. That's why this minus 40 dB becomes minus 20 dB. Therefore, this contributes here numerator first order factor at the corner frequency of omega 2. Then again, the slope is changed from minus 20 dB to minus 40 dB. Another first order factor is there, the denominator. So, two first order factors in the denominator, one first order factor in the numerator, one s factor in the denominator, one k is there. All we have to find. That is called the transfer function of given system. But here, if we know the corner frequencies, then we can find all transfer functions. But omega 1 is not given, omega 2 is given, omega 3 not given. Omega 1 does not given. Omega 1 means omega 1 equal to 1 by tau 1. Omega 2 equal to 1 by tau 2. Omega 3 equal to 1 by tau 3. 3 time constants. This time constant is in the numerator. This and this are the denominator. Because this factor is in the numerator already we have seen. So 1 by tau 1 we do not know. Omega 1 we have to find. But omega 2 is given. Therefore tau 2 we can find. Omega 1 by tau 2 equal to 1 by omega 2. 1 by 8. That's all. Omega 3 also not given. So, finding k, omega 1, omega 3 is the solution. Finding, so now I can write the transfer function. K, numerator factor, tau 2 s plus 1. Tau 2 equal to what? 1 by omega 2. The denominator, s multiplied by tau 1 s plus 1 multiplied by tau 3 s plus 1. I have to find a tau 2, tau 3, k, that's all. Already tau 2 is found already. Because omega 2 is given 8, is given in the sum itself. All other constants, that is omega 1, omega 2 and k has to be found. That's all. So we have to prepare a table. From point 1 to omega 1, the slope is minus 20 dB. The slope contribution is in the reverse order we have to write. Whatever you wrote for Bode Plot, you have to write in the reverse order. Point 1 to omega 1, minus 20 dB. Slope contributed minus 20 dB. Corner frequency nil. The term is k by s. That's all. K by s. Because it is not passing through 0 dB. That's why k by s. If it is passing through 0 dB, so 1 by s. It is not passing through 0 dB, therefore k by s. Omega 1 to omega 2. Omega 2 is given 8. The slope is minus 40. Already minus 20. Minus 40 means this contribution. By this factor is minus 20 dB. That is tau 1 is 1 by omega 1. The factor is 1 by 1 plus tau 1. Yes, that's all. Next is omega 2 to omega 3. Slope is minus 20. Already this is minus 20. Here contribution is minus 20. Net slope is minus 20. Already it is minus 40. Already minus 40. Now minus 20. So numerator factor is there. That's why it is changed from minus 40 to minus 20. Therefore plus 20. This is the numerator factor. That is T2. 1 plus T2 is in the numerator. Because the net slope is changed from minus 40 to minus 20. Therefore this slope contributes plus 20 dB per decade. Next is from omega 2 to infinity. The net slope is 40. Earlier it is 20. Now it becomes 40. Therefore another first order factor minus 20 dB per decade. That is T3 equal to 1 by omega 3. The next factor is 1 by 1 plus T3s. So now what and all known? We know omega 2 is 8. That we know. This alone we know. T2 can be found. T2 equal to 1 by 8. We can substitute. But we do not know K, we do not know T1, we do not know T3. Finding these three constants is the sum. That's all. Here we know. At omega equal to 4, 0 dB. Here, what is the slope? Slope is minus 40. This we do not know. Y2 we do not know. Net slope we know. Y1 we know. Y1 is what? 0 dB. Omega 1 is 4. X2 we do not know. But substituting in that formula, we will get one coordinate. Here the magnitude is given 36. Here magnitude is given. Here magnitude is given. Here coordinate is not x coordinate is not given. Here x coordinate is given. So we can find that formula. Already we have seen one formula that y2 equal to net slope multiplied by omega 2 by omega 1 plus y1. That formula. In the formula, if we substitute, omega 1 can be found. One constant is known. Here, if you come here the magnitude is not given. Magnitude is not given. If the magnitude is given, here the magnitude is given 21 dB. This magnitude is given. This point is unknown. This point is known. If we know this magnitude, we can find this by using that same formula. But here magnitude is not given. For that, the critical thing is, what is the distance between these two? 4, 8, 1 octave. 1 octave. What is the slope here? 40 dB per decade. If it is octave means what is the slope? 1 octave means what is the slope? 1 octave means 20 dB per decade means 1 octave means 12 dB per decade. Per octave. So 40 means double. 24 dB per octave. 24 dB per octave. That's all. So degree here 0. Therefore here minus 24. That's all. Minus 24. Here we know both coordinates. 8 we know. Magnitude is minus 24. We substitute that. We can find this omega 3. That's all. The sum is over. We know omega 1, omega 2 and k we know. Sum is over. 0.5 we got. Omega 1 equal to 0.5. Magnitude also here we know 36. So using this for this slope, what is the magnitude here? 20 log k by omega equal to 36. Here omega equal to 0.5. That's all. Omega equal to 0.5. That formula is used. Once again I am telling. Here omega already we found 0.5. 20 log k by omega equal to 36. Omega 1 is 0.5. K we do not know. Equal to 36. From that we can find k. So all three unknowns are found. That is all. That's all. In that way, we can find the transfer function from given Bode plot. Yes. Therefore, k equal to 31.623 and tau 2 is 0.125 because 1 by 8, tau 1 and tau 3 all we found. Therefore, this is the transfer function of given Bode plot.